Let's look at some more examples of Laplace transforms. These will not only illustrate the transform itself, but we'll use them as examples of some of the properties of Laplace transforms that we're going to look at shortly. So let's start with one that I actually went over in one of week 2's live meetings. It's what we call a unit ramp. So this is the case where our function f of t for non-negative values of t is equal to t itself, and for negative values of t is 0. So the graph looks like this. So as I said, we went through this in one of last week's live meetings. Let's go through it again quickly. F of s then is going to be the integral from minus infinity to infinity of f of t e to the minus st dt, as always. But as will often be the case, in this case our function is 0, as the value 0, when t is less than 0. So we can integrate from 0 to t. T e to the minus st dt. And we'll do the integration using integration by parts. So how to do this, we will we'll do integration by parts. So we're going to want to say that u is t, and dv is e to the minus st dt, in which case du will be dt, and v will be minus 1 over s e to the minus st. So in that case, our integral will be minus 1 over s t e to the minus st, evaluated at the limits of integration, minus v du, so that will give us plus the integral from 0 to infinity of 1 over s e to the minus st dt. Now, when will this converge? The first term will diverge as t goes to infinity unless the real part of s is positive. But if that is the case, if the real part of s is positive, then this will give us 0. As t goes to infinity, 1 over st e to the minus st will converge to 0. And likewise, as t goes to 0, this quantity will go to 0. So the first term vanishes. And we know that Well, this second term is 1 over s times the integral e to the minus st dt. And that integral, of course, is just the transform of a unit step. So we're left with 1 over s squared in the end, the transform of a unit step being 1 over s. So the region of convergence is the right half plane where the real part of s is 0, and the transform itself is equal to 1 over s squared when it converges. So that's this example of a unit ramp. Okay, so let's go on to another example. I should say, in this case, we said that the function was going to be zero valued when t is negative, and we will often be looking at functions of that sort. The Laplace transform is often used to study things like transient behavior, when something suddenly happens at t equals 0 and you wish to see how a system responds, for instance. So we will mainly be interested in so-called one-sided functions. And for that reason, we'll use the one-sided or unilateral Laplace transforms. So by one-sided functions, we mean functions for which f of t equals 0 for t less than 0. So we'll use the one-sided or unilateral Laplace transform. That means we'll take f of s to be, well, f of s, which we can also write again as script L followed by ft in curly brackets, which is by definition the integral from 0 minus to infinity of ft e to the minus st dt. A little more notation related to one-sided functions. And in this case, we'll introduce some notation for the unit step function, which was the first function that we looked at when we started computing Laplace transforms. We're going to denote the unit step function This is another thing that I mentioned during the last live meeting. We'll denote it u minus 1 of t. And you can think of the minus 1 as corresponding to the fact that the Laplace transform of this unit step is 1 over s, or in other words, s to the power minus 1. It's just handy to bring in a special notation for the unit step. That's partly because it's an important function in engineering. It's an important sort of test signal that we often use as an input to systems. But it's also useful to us right now because we're going to be talking about one-sided functions. So this is handy notation for representing one-sided functions. So for instance, this way, the unit ramp, whose transform we just calculated, can be denoted as follows. So instead of talking about the two cases where t is negative and t is non-negative, we can simply multiply by the unit step a function that takes the proper values when t is non-negative. So we'll represent functions, our one-sided functions, often in terms of the unit step function. Let's take a look at another example of a Laplace transform. This is going to be a version of the unit step that is shifted in time. So u minus 1 of t minus capital T. Let's suppose that t is positive. In that case, the graph of this function looks something like this. Function 0 until little t equals t, and then it jumps up. Then we get our unit step. So our function looks like that. Now we're going to derive a property of the Laplace transform that explains what happens when you shift a function in time, what happens to its Laplace transform when you shift a function in time. But for the purpose of this example, we're just going to use direct calculation. So the transform of this function, this of course is a one-sided function, so we can just write down our unilateral Laplace transform integral. But in this case, of course, the function is going to vanish until t is greater than or equal to capital T. So we can simply start our integration at capital T. And it's when t is greater than or equal to capital T that the function will be equal to 1. So the integral will be e to the minus st dt. Okay, so what do we get for this integral? Well, the antiderivative of e to the minus st is e to the minus st over minus s. What happens if we evaluate that at our limits of integration? Well, this integral again is going to converge if and only if the real part of s is positive. Let's see, yeah. If the real part of s is 0, then at least in the case where s is equal to 0, we have a problem because we're dividing by 0. So this is going to give us 0 if the real part of s is positive. We subtract from that the value that we get when s is equal to capital T, and that gives us e to the minus s capital T over s. So what we end up with is e to the minus s capital T times 1 over s. And again, that's in the case where the real part of s is positive. So what we have is the transform of our original unit step, but then corresponding to the shifting in time, we have another factor e to the minus s capital T in front of the transform. And we'll see shortly when we look at properties of the Laplace transform that this is a general result. If we shift f of t to the right by an amount capital T, then the transform of the resulting function is the transform of the unshifted function times this factor e to the minus s capital T. So multiplying by this exponential e to the minus s capital T in the Laplace domain, if you like, corresponds to shifting a function in the time domain to the right by an amount capital T. Let's take a look at another example that will illustrate one of the properties we're about to derive. This is an example of a trigonometric function, in particular a sinusoid. So again, we're focusing on one-sided functions from now on, so we can just write it as sine omega t times the unit step. Now, as I think I've said before, I certainly emphasized it in the live meetings, we're computing a lot of integrals here in order to develop these initial examples of Laplace transforms, but in practice we're not really going to have to do any integration. And here already we can stop doing integration because we've already found the Laplace transform of an exponential, and we can simply represent this sign in terms of exponentials. Sine omega t is, of course, e to the j omega t minus e to the minus j omega t divided by 2j. Okay. But we've already found the Laplace transform of a one-sided exponential. We saw that the transform of e to the at times the unit step is just 1 over s minus a. So in fact what this will give us, by the fact that the Laplace transform is linear, we can simply consider the two exponentials separately. So the first one will give us 1 over 2j. Again, that's because of the linearity of the Laplace transform. We can take the constant 1 over 2j out front. And the transform of e to the j omega t times u minus 1 of t will simply give us 1 over s minus j omega. So the first exponential will give us 1 over 2j times s minus j omega. The second, by the same token, will give us 1 over 2j times 1 over s plus j omega. And simplifying that, we will get 1 over 2j times 2j omega over s squared plus omega squared, which simply works out to omega over s squared plus omega squared. So there is the Laplace transform of a one-sided sinusoid. Obviously, this is going to be a very important function for us. Sinusoidal functions being very important in the study of dynamical systems. So there are some more examples of Laplace transforms, and in this last example we actually exploited the property of linearity of the Laplace transform. That's going to be the first one in our list of basic properties of Laplace transforms. But there are others which we've already illustrated as well. I mentioned that this is going to be an example of a general property when we shift a function to the right by an amount capital T. In the Laplace domain we multiply its transform by e to the minus s capital T. So let's end this video here, and in the next one we'll start looking at the key properties of the Laplace transform, such as linearity and such as this time shift property. See you in the next lecture.